Friends, good morning. So, as you know, we have completed 3 chapters from our syllabus. That is current electricity, third chapter, and the alternating current and the electromagnetic waves. So, in the last class, I have revised the electromagnetic waves chapter. I hope you have understood it very well and you don't have any doubts. If you have any doubts in electromagnetic waves, just ask me. Don't be there with doubts. Okay, get them clear first. So, in today's class, I wish to revise the third chapter, current electricity. Okay, so this was the first chapter which we studied. I thought you may have forgotten that. That's why I thought of revising this. So let revise this chapter briefly. Okay, so in this current electricity chapter, we have started it with the definition of what exactly is electric current. Electric current is defined as the rate of flow of electric charges through a cross section of a conductor. Means when in an conductor the electric charges flows, that will constitute an electric current. For that we have also given the formula also. This is the formula for electric current, that is I is equal to dq by dt. I is equal to dq by dt is the formula for electric current, where that q is what? The charge flowing, the total charge flowing. We have given it as I is equal to q divided by t, that is the total charge flowing divided by time taken. But here the rate of change of charge with respect to time we have given. Next, current is a scalar quantity. Yes, it is having the direction, but it will not uh, obey any laws of vectors. Hence it is a scalar quantity, and current is having a unit ampere, which is denoted by capital A. Okay, after that we have studied some important definitions related to this current electricity. That is, we've gone with the electric current density, we gone with the drift velocity, mobility. Okay, we have studied them. So okay, now just think, what is that? Current density is nothing but J is equal to I by A, means the ratio of the current to the area. Means we can define it as the current flowing normally per unit area of cross section. So by using this formula, you can write the SI unit for this current density as ampere per meter square. That is, current is measured in terms of ampere and area is meter square. Next, one more quantity we studied, that is drift velocity. Means it is nothing but one what? Average velocity. Drift velocity is nothing but one average velocity with which the charge carriers or the free electrons are nothing but the charge carriers. The charge carriers or the electrons get drifted in a opposite direction to the applied electric field. Means we have studied this in detail, that in any conductor, if we are applying the electric field in some direction, the electrons will get drifted in the opposite direction. So that velocity with which, that average velocity with which the electrons will get drifted in the direction opposite to the direction of applied electric field is called as what? Drift velocity. And when that electrons are moving with respect to that velocity, they will produce some acceleration. So that acceleration stays for a short time. Okay, when that electron collides with some vibrating ion, means whenever the electrons are moving with a drift velocity, that electrons, when they collide with any ions, what happens there? Collision happens between an electron and one ion and vibrating ion. So this small interval of time between collisions of electron and ion in the conductor is called as what? Relaxation time. Means a small interval of time between the two successive collisions of ions and the electrons is called as what? Relaxation time. You just go on looking at the notes here. I'm talking about relaxation time. I'm talking about relaxation time. Okay, now next, the mobility is nothing but what? The ratio of drift velocity to the electric field. See here. Okay, so the mobility of free electrons is defined as the magnitude of the drift velocity per unit electric field. Understood? Mobility is nothing but magnitude of drift velocity per unit electric field. Next, we'll come across important definition, that is resistance. We have discussed this in the class in detail. So here after the mobility, we gone through some relation between drift velocity and electric current also, that is q is equal to I is equal to NEAVD. That also one derivation is there, you go through that also. Okay, I think you may have this in the notes. Okay, so resistance. So what is resistance? We got this resistance when we are studying about Ohm's law. When we are studying about Ohm's law, which says that the current flowing through the conductor is directly proportional to the potential difference across the conductor. So we have written I is directly proportional to V, and then we got this R. R is nothing but electrical resistance. Understood? So what is this resistance? This is the opposition offered by a conductor to the flow of charges. Means whenever the charges are moving in the conductor, what happens over there? The free electrons are traveling from negative terminal to the positive terminal. So this gives rise to electric current. So when free electrons flow from one end to another end of the conductor, they collide with some ions in that conductor. Understood? Because of this collision only, we are getting the opposition to the flow of electric charges. So whatever that opposition we got over there in the conductor, that only is called as what? Resistance. Means because of the collision in electrons and ions, we will get the opposition to the flow of charges, that is called as resistance. The opposition offered by the conductor to the flow of charges. So this is defined as the ratio of V to I, means what is the potential difference to the conductor. Okay, next, SI unit of electrical resistance is ohm, that you know already. Resistance is directly proportional to length of the conductor, yes, and it is inversely proportional to area of the conductor. Hence we will get a constant there, and that constant is called as what? Resistivity. Understood? And how can we define this resistivity? That electrical resistivity rho is numerically equal to resistance R. But when that becomes equal, it becomes equal to R when L is equal to 1 centimeter and A is equal to 1 centimeter square. Means unit length and unit area when you get, at that time the resistance becomes equal to the this resistivity. Okay, the unit of resistivity is ohm meter. The resistance we measure in terms of ohm, and resistivity is ohm meter. Understood? So some resistivity, how the resistivity of materials depends on the material and its temperature, that is given. The materials like manganese and constantan have low temperature coefficient of resistivity. Hence they are used to construct the standard resistors. Okay, so here we have taken some graphs of which shows the variation of resistivity with respect to temperature. That is, we are having one copper graph, nichrome and semiconductors. Okay, that is some extra information. Next, moving on, we are having some factors affecting resistivity, dependence of resistivity and the temperature. Okay, we have studied all these things. So, electromotive force. What is electromotive force or EMF? EMF is nothing but what? EMF of a cell is defined as the potential difference between the positive and negative electrodes of the cell when the cell is in open circuit. Means whenever means it may be defined as the potential difference between its terminals when there is no current drawing from the cell. Means from any cell when we are not getting any current, what is the difference between the two terminals? That is electromotive force. Next, internal resistance of a cell. The resistance offered by the cell to the flow of current through itself. Means internally whatever the opposition is offering for the flow of charges in a cell, that is called as what? Internal resistance, and that we can represent with respect to small r. Okay, these are the important definitions when you are studying a cell. Cell is a device which is having two terminals, positive and negative, is used to draw the current. And next, terminal potential difference. Here we have shown a cell current, when how the current is drawing from the cell, that we have shown, and current drawn from the cell is given by the expression I is equal to epsilon divided by r plus r, capital E divided by r plus r. E can be written as the EMF of the cell. Next, so here they have shown some equivalent form of Ohm's law or relation between current density and electric field. See here, they have considered one conductor and let L be the length of the conductor, and it is having a area capital A, and rho is the resistivity of the material. Then from the resistivity formula you already know this, R is equal to rho into L by A. So current per unit area, I by A is nothing but what? Current density, and it is denoted by J. So what we have according to Ohm's law, we have V is equal to I into R. Understood? So in the place of R we are substituting this, R is equal to rho into L divided by A. So I by A is nothing but what? J. So J rho L we got, but this V is nothing but what? V by L, because potential difference with respect to length we are getting, and this capital E in the place of V we can write J rho L. So J rho L divided by L, so J into P, but J is equal to E divided by rho. So 1 by rho is nothing but this sigma, and J is equal to sigma into E. This is called as equivalent form of Ohm's law. Understood? So here they have given some expression for drift velocity. Means up to here we have discussed about small definitions. Now here we will discuss the derivations coming in this chapter. See here, expression for drift velocity they have given. What all the derivations come in this chapter? See. The average velocity with which electrons drift, that is definition, you know it. That is definition of the drift velocity. Okay, so the acceleration of the electron in presence of the electric field is F is equal to m into A, that we know from the Newton's second law. Vi be the velocity of ith electron and after the previous collision, then its velocity just before next collision is ti seconds. So Vt is equal to Vi minus E into E divided by m into Ti. This is something different. In our notes I have given it in detail, you refer that. Okay, so expression for electrical conductivity they have given. What is expression for electrical conductivity? With respect to the expression for drift velocity, they have taken charge flowing through the conductor is Q is equal to I into T. So that they are substituting in the previous definition, what? So we know Q is equal to I into T. So this thing they are substituting here, and we already know that the current density is nothing but I is equal to J into A. So at the place of I, they have written J and taken A to this side and just adjusting the terms. So here we got J is equal to N E square tau by M into E. But we know that J is equal to sigma into E. This is what equivalent form of Ohm's law. Substituting that here, we will get sigma is equal to N E square tau by M. This is the expression for electrical conductivity. Understood? Next, we are having the expression for current in terms of drift velocity. This derivation also I have told. Q is equal to NAE into Vd we are having, that is delta x. They are given in some tricky form. Ohm's law, you know it very well, that the statement of Ohm's law says the current through a conductor is directly proportional to potential difference between its ends. Understood? So we can write, by the statement we can write I is directly proportional to V, and to remove that proportionality sign and to have some equality, we have introduced R, and that R is nothing but what? Electrical resistance. And I also told you some limitations of Ohm's law. Here they have given only 2. There maybe I have given up to 4 limitations of Ohm's law. You read that in detail. So this is what color coding of the resistance means. This is a resistor, a small device which is having a property of resistance. On every resistor we will be having some colors given. So what that colors indicates, to understand that we are having a method of color coding. Means one code we are having, B.B. Roy of Great Britain had a very good wife, like this, BBR, like this we are writing what? Here we are writing the colors first. With respect to that we have given some numbers 0 to 9, and gold, silver and no colors means what the fourth band indicates. Up to this we are having the colors, but when there are gold or silver or there is any no color for the fourth band, what we have to understand, that is given here, that is tolerance. Understood? So this method also I have explained in detail. I had made a special video for this only. So these are some examples we are having. Okay, next, equivalent resistance for two resistors in series. This is very important derivations we are having, means for the series combination also and for the parallel combination also. The equivalent resistance derivation is very important. Here see, two resistors are connected in series. In the current in the series combination, the current flowing is same, but the potential difference is different. You know that already. Okay, so the potential difference across potential difference across R1 is this R1 V1, R1 is equal to IR1, V2 is equal to IR2. Adding them, I is equal to R1 plus R2. So in the place of R1 and R2, we are writing a equivalent resistance. Hence it is a series combination. We will write it RS. So we are getting V is equal to I RS. So from the equation 3 and 4 you can write that RS is equal to R1 plus R2. So when the resistors are connected in series, the equivalent resistance will be like this, and they have given when two resistors are connected in series, the equivalent resistance will be greater than both of the resistance, because here by adding R1 and R2 we are getting RS. Hence obviously the equivalent resistance is greater than the individual resistances. Now when you are connecting the series the resistors in parallel, see here, this is the parallel combination of the series where the potential difference between these two is same. Potential difference across R1 and potential difference across R2, they are same, but the current flowing in both of the resistance is different. Hence we can write the currents here. I1 is equal to VR1, I2 is equal to V by R2. Now add both of them. You will get V by R1 plus V by R2, taking V common, this. Now you compare. In the place of 1 by R1 plus 1 by R2, we will write 1 by RP. So by comparing 3 and 4, we will get 1 by RP is equal to 1 by R1 plus R2. So or also you can write it like this. This is the equivalent resistance for the parallel combination of the resistances. Okay, and this sentence is very important. When two resistors are connected in parallel, the equivalent resistance will be lesser. But in the parallel series combination, what we obtained there, we got when two resistors are connected in series, the equivalent resistor is greater than both of the resistances. These are the things you have to remember. So now see here, what happens when cells are in series and when cells are in parallel. See here, two cells we have connected in parallel in this example, and this is in series and parallel. So what happens here, see here, in this series combination of the cells, the potential difference between A and B, these 2 points, and the potential difference between B and C we have considered, that is E1 minus IR1 and E2 minus IR2. So the potential difference between A and C whole, if you consider, you have to add both of them. So VAC will give this. So taking E1 and E2 one side and R1 and R2 another side, you will get VAC is equal to E1 plus E2 minus I into R1 plus R2. So the equivalent circuit, so consider this equivalent circuit, and it is having the internal resistance R equivalent and the EMF is E equivalent. So for that we will get VAC is equal to E equivalent minus IR equivalent. So here R equivalent is R1 plus R2, E equivalent is E1 plus E2. This is the cells in series. Now what happens when cells are in parallel? See here. Here we are having the potential at B1 and B2, that is VB1 and VB2. So the potential difference across the first cell is V is equal to E1 minus I1 R1, and that I1 you can write it as E1 divided by R1 minus V R1. The same way you can write this also. Now add I1 and I2. You will get like this. Okay. Now combine all of them, E1 and E2 one side and V one side. So E1 by R1 plus E2 by R2 minus V into 1 by R1 plus R2. And here we are having the equivalent EMF and equivalent internal resistance. So comparing, so this is I. So what V becomes now? V is equal to E equivalent minus I into R equivalent. Means this is VAC. This equivalent resistance we have considered here, and comparing equation 3 and 4 we will get the equivalent EMF and the equivalent resistance. All these things I have discussed, I am just revising. So now Kirchhoffs laws are there, Kirchhoffs current law and Kirchhoffs voltage law. So what happens in the first law? Here we have considered the different currents meeting at a point. So sum of all these currents entering one junction is equal to the sum of currents leaving the junction. Means input current is equal to output current. Means whatever I1 is input, I2 is input and I5 is input. So I1 plus I3 plus I5 equal to I3 plus I4. So taking them here you will get 0. This is the Kirchhoff's first law, and this is based on the law of conservation of charges. Next, Kirchhoff's voltage law, or also we can call it as a Kirchhoff's loop law. So here what happens? Here the algebraic sum of the charges in potential around any closed loop containing the resistors and the cells in the loop is 0. Means in this particular circuit, if you consider the algebraic sum of the charges in potential and the resistors is equal to 0. Means IR products, you can say the IR products of these circuits, the addition, the algebraic sum of IR products is equal to the okay. So in this circuit we are having some voltages also and some potential and some EMFs also. So the algebraic sum of all the voltages, that is the potential differences across all the elements, and EMFs of all the sources in any closed electric circuit is equal to 0. This is about what? Kirchhoff's second law. And Kirchhoff's second law is based on the law of conservation of energy. Now next, after this we discussed some instruments like Wheatstone's bridge, potentiometer. Okay, so in the Wheatstone's bridge we have applied KCL and KVL, Kirchhoff's current law and Kirchhoff's voltage law. What we have considered? We considered 4 resistors, R1, R2, R2, R3 and R4, that we have set in type of a Wheatstone, and here we have taken one galvanometer, we have connected it. The current through the galvanometer is 0. So at the junction B, what happens? I4 equal to I2, means incoming current is equal to outgoing according to Kirchhoff's current law. And at the junction D also same, I1 is equal to I3. Okay, so now applying Kirchhoff's voltage law to the loop A, B, D and A, means to this loop if you apply the Kirchhoff's voltage law, what you will get? Here from A to B, if you are going, I2 plus R2 we are having. Now next come here, Ig we are having, the resistance is R2 same, but current is Ig, that is 0. And again go back here, in the opposite direction you are going, hence it is minus I1 R1 equal to 0. So what happens here? I2 R2 equal to I1 R1. This is in this loop. Okay. Next, you consider the same loop B, C, D, B. This loop you consider, means closed path you consider. So here go from here I4 R4. Okay, again go here. It is in opposite direction, hence I3 R3. Again going here plus Ig into R3, but Ig is 0, hence here I4 R4 is equal to I3 R3. Now equation 4 divided by equation 3 they have done, and according to 1 and 2 what we are having, I4 is equal to I2 and I3 is equal to I1. Hence what we get, I4 R2 divided by I4 R4 is equal to I3 R1 divided by I3 R3. That is nothing but what, R2 divided by R4 into R1 divided by R3. Means in this Wheatstone's bridge what we are having, we are proving one balancing condition which we have obtained already. Next we are having potentiometer also, that we have studied in detail in the theory classes. Okay, now after this let's see how is the working of this. So this meter bridge works on the principle of Wheatstone's network, and it is used to find the value of unknown resistances, and the potential is used to compare the EMF of two cells, and it is used to find the internal resistance of the cells. And these are all the formula we obtained in this chapter, and also we have solved some problems there. Okay, so I have just briefly revised this current electricity chapter by using some notes, some printed notes. Okay, if you still have any doubt in the current electricity chapter, you please contact me and get that doubts cleared. Okay, and try to solve some more problems also. We have solved enough problems on that, but try to solve some more problems. And if you have any doubts, again contact me. Thank you. If you want any other topic to be revised once again, you can also ask for that. Okay, thank you.